All right, so uh, we want to obviously be able to implement this in Verilog, uh, and we already have our code for our full adder. Right, it looks like this here, and so what we want to do is we want to make multiple instances of the full adder and connect them together, or namely, we're going to be doing instantiation, making instances, making copies of these full adders. And so, whenever I'm doing a problem that involves some instantiation, what I always do is sketch the way the modules are interconnected and label all the signals. So specifically here, I've got a few things that are ambiguously named, right? So I've got the inputs for all these full adders in terms of the A's and B's kind of labeled uniquely, right? I've got A3, B3, A2, B2. So these could almost be thought of as an index of a vector for these numbers. But my carries I don't really have uniquely named. So let's name them. Let's say let's do a different color here. We'll do purple. Well, of course we'll call this one C in, right? This is our C in from maybe, right. We could take this concept of a full adder being copied to make a 4-bit adder. We could also take 4-bit adders and link them together and make an 8-bit adder or 16-bit adder. So that also means that this must be our final C out. Now we need to name these intermediate signals. Of course, this is C out for this adder, but it's C in for this one. So maybe I'll just do this, and I'll just call it. We'll call it C1, C2, and C3. There's a reason why I'm starting at C1 because technically this here is considered C0, but I could call it C0 as well, but it's more correct to call this C1. So everything else is named, right? Our sum, we've got that named. So I think we're good to start doing this in Verilog. So we're gonna have our thing here. We're gonna say module add add 4 bits. And what are we gonna have? Well, we're actually pretty much gonna have the same signals as the full adder. We're gonna have A, B, C in, C out, and a sum. And I can also copy these can copy them. A and B are 4-bit vectors. So that means we've really got 3:0. C, or carry in and carry out, are single bits. So that means that these need to go on their own line, right? So we're going to have input C in, and that's it for C in, right? It's only a single bit. Same with output, right? S is a 4-bit signal, right? So from 3 to 0. And we've also got just C out, which is a single bit. And let's throw our end module in here. All right. Now we can start doing our instantiation. Almost. Sorry, I take that back. We can almost start doing it. There's one more thing that we're missing. If we go back to our sketch, we see that these signals, right, these become outputs, these become outputs, these are all inputs, and this is an input. But what about these guys? These 3 signals here. These guys are internal to our 4-bit adder, meaning that they never actually get broken out, and we're never really going to look at them. So what that means is these are wires, right? They're internal variables or wires. So what we need to do is declare them as such. We're going to say wire, excuse me, and we're going to, oops, should I space it over? Wire, and so based on our indexes for a sketch here, we've got 3 through 1. So I'm going to follow that, and I'm going to say 3 through 1. And we'll just call this C, right? These are just our kind of internal carries. And now, I'm going to remove this space because you don't have a lot of space to work with here. Now we can do our instantiation. So the way our instantiation works is we start off with our the name of our module, which in this case we're going to say is FA, full adder, right? That's what the name is. And then we're going to give this specific instance a unique name. So in this case, I'm just going to call it stage 0, right? So that means this, here, let's label them here. This is stage 0, stage 1, stage 2, and stage 3. All right, and now we need to connect some signals in here. And the way I like to do it is just keep things in order. There are other ways to actually bring in arguments when you're instantiating, basically saying A equals something, B equals something. But I usually just keep them in order. So that means here, since this is our first stage, we need to snatch off the first bit of A, which the first bit is index 0. And then we need to do the same thing with B. And then the next thing is C in. So for stage 0, let's look at it. Our input is C in. So here I can just keep C in. And our C out, let's look back at our sketch. C out is connected to C1. C out for this module is connected to C1. So we're going to just do C1. And then S, of course, is just going to go to S, or the least significant bit of our sum, which is S0. And there we go. That's the instantiation for this guy. You need to do that 4 more times. So I'm going to copy this line because I'm going to end up inevitably copying it. This is stage 1. And so that means that we're adding the second bit, which is an index of 1 of A and B. And now what is our carry in for this specific module? Well, it looks like our carry in is C1, right? Our carry in for stage 1 is C1. So let's take that guy there. And next, right, looking at this, we need to put our carry out in there. Our carry out is what? Our carry out is C2. And finally, our sum just goes to bit 1, which is the second least significant bit of sum. Hopefully you're starting to see the trend here, right? I'm just following along with my diagram here and making sure that I'm keeping things in the same order as these arguments. All right. Let's copy this guy. And of course, we're gonna, actually, maybe it makes more sense to copy this for this guy. So we're going to increment this by 1, increment this by 1. This is going to output, or this input is going to be carry 2, and its carry out is going to be carry 3. And of course, its sum is going to be to bit 2. Make sure we got a different name here, C2. I'll copy this guy. And now we can do our final stage here. So our final stage is stage 3. its inputs are the most significant bits of A and B, and its carry in is C3. Its carry out is simply the carry out bit, so it's actually an output here. So we'll call this guy C out. And finally, our sum is to bit 3. So there we go. That's how we do instantiation, right? We're making multiple copies of this full adder module. And when I say copies, I mean actual copies. These assign statements here, these data flow statements, they are going to make some hardware circuits, right? So we got some exclusive OR gates, some ANDs, and some ORs. It's going to make those connections, and it's going to copy them 4 times and connect things according to the way that we've got it instantiated.